Welcome to EconTalk, part of the Library of Economics and Liberty. I'm your host, Russ Roberts of Stanford University's Hoover Institution. Our website is econtalk.org, where you can subscribe, comment on this podcast, and find links and other information related to today's conversation. You'll also find our archives, where you can listen to every episode we've ever done going back to 2006. Our email address is mail@econtalk.org. We'd love to hear from you. Today is May 2nd, 2016, and my guest is Pedro Domingos of the University of Washington, and author of The Master Algorithm, How the Quest for the Ultimate Learning Machine Will Remake Our World. Pedro, welcome to EconTalk.
Thanks for having me.
So this book is an introduction to machine learning. It's an introduction to a world that actually we're all immersed in without realizing it, most of us, as well as its implications for our lives and the future of humanity. It's a really fascinating book. We're going to go through its main ideas today. Let's start with the most basic one. What is machine learning?
Machine learning is computers programming themselves instead of having to be programmed by us. In the first stage of the information age, we had to, tell computers what to do, right? So most of the things that people see computers doing, somebody actually wrote a program in painstaking detail explaining to the computer exactly what to do step by step. And this is very slow and costly and so limits, the rate of progress and what computers can do. The new idea in machine learning, and it's a very powerful one, is that we don't actually have to program the computers anymore. They look at the data that we generate, and from that data, they try to figure out what to do. Like, for example, a recommender system, say Amazon's or Netflix's, from the things that you've bought or clicked on and that other people have bought or clicked on, will try to predict what it is that you want to buy and then recommend that to you.
You describe it as a technology that builds itself, an artifact that designs other artifacts. That gives it a sort of volitional consciousness, but it doesn't. These exercises by computers don't have a will of their own. We still have to tell them a goal. So we're not writing the code, but we're telling them something. The programmers are telling them something that they want to accomplish, correct?
Yeah, exactly. So in some sense, what we're doing is programming them at a higher level, right? We just tell them in general terms what it is that we want them to do, and then we let them figure out by themselves how to do it. And then the whole trick becomes, well, how do we set their goals? But you're right. These machine learning programs, however much they learn, they do not have goals of their own. It is still our job to tell them what the goal should be.
Now, something like recommendations for Amazon or Netflix, I think in the back of our minds, most of us have some idea of how that would happen. We know it has something to do with looking at other people like us and seeing what they liked and then figuring we'll probably like it too. And when you actually have to figure out how to make that happen, it's not so straightforward. And a chunk of the book is about that, as well as other challenges. But can you give us some other examples, which you do in the book, of what these kind of algorithms are helping us with or are doing for us online that we're not probably aware of?
Yeah, so first of all, there are the online things, which is actually where people have, for the most part, met machine learning, although they may not be aware of it. But it's not just recommender systems. When you do a web search, Google or Bing use machine learning to figure out what results to give to you. When you go to Facebook uses machine learning to figure out what updates to show to you. Twitter uses it for tweets. Just about everything. For example, online dating sites, they actually use machine learning to propose potential dates to people. And these days, a third of all marriages start on the internet, so there are actually children alive today that wouldn't have been born if not for machine learning. But it's not just online; it's also in real life, if you will. So just as an example, a self-driving car is essentially powered by machine learning algorithms. We actually don't know how to program a car to drive itself. It learns by observing people and the road and trying to figure out how steering and braking and whatnot follow from what the camera and the other sensors are showing. But even other things like your smartphone. Your smartphone is full of machine learning algorithms. They do the speech recognition. They do the spelling correction. They choose what things to show you at what time. As another example, a lot of stock picking these days, a lot of things in finance are done by machine learning. Companies use machine learning to screen job applicants. So some people have or don't have a job because a machine learning algorithm decided that they looked good or not. And same thing with getting raises. Medical diagnosis, machine learning algorithms are actually typically better than human doctors at diagnosing, various things, like, for example, deciding by looking at an X-ray whether there's a tumor in somebody's chest or not, and so on. The list is really endless.
A lot of the examples you gave, I don't know if this is just by chance, and I didn't feel this when I was reading your book, but a lot of the examples that you give are examples of what I would call matching. The dating is an obvious example, but so is really Netflix and Amazon. You're trying to match me with movies or books or products that I would be likely to buy. What is that a huge portion of the use and application of machine learning, or am I just happen to
yes,
is that
indeed.
a coincidence?
No, it's not a coincidence. So all of these applications are instances of really the same phenomenon, which is, the internet has created this world of infinite choice where anybody can buy anything from anybody, anywhere, at any time. And this is great, but what it creates is a problem of too many choices, right? If you want to buy a book and you go to Barnes & Noble, you go to the relevant section, let's say mystery books, and you can actually take a look at all of them because there's maybe only 500 or not even. Whereas, on Amazon, there's, who knows, maybe 1 million. And therefore, something else needs to come in to help you make those choices, and that something else is machine learning. So in a way, machine learning is kind of like the next logical step from the internet. The internet creates all these choices because it puts everybody in contact with everybody, but then what machine learning does is it actually lets you make those choices without having to look at every item yourself. In some sense, what the machine learning algorithm is trying to do is, for example, pick out the books that you would have picked out if you were able to look through all 500,000 of them. So, there's this notion of the long tail, right, and how the internet has made it possible for, people to buy things from the long tail. But that can really only happen once there's a way for you to explore the long tail. It is long, and machine learning is what does that for us.
But there's a lot bigger promise. It's interesting that a lot of life is about matching. You gave an example that I think of as filtering, but it really is matching also, right? It's how do I match what I'm interested in to the how do I pair and get rid of stuff that I'm not so interested in and match what I am interested to my time.
Yeah, and matching buyers and sellers, right? In a way, what machine learning does is it makes the economy work more smoothly, because the problem of matching, there's this sort of like in economics, there's this abstraction, right? That there's a market and all buyers can talk to all sellers, but the devil is in the details. The interesting thing is that machine learning actually makes that closer to being possible than at any time before. So, some things are matching people with items, some things are matching people with other people. So there are various versions of this with different flavors and different constraints on them. But a very interesting example of all this is the market for ads online. Right? When you see a web page or search results, you get a bunch of ads. And those ads are actually selected in a fraction of a second by an auction among all all the possible ads that could be shown. And then based on all those, on all the ads, based on the content of the ads and on the text of the page and whatever, the ad network like Google knows about you as a user, and also what different, advertisers are willing to pay for the slot, it actually runs the auction to decide, what to show to you. And the machine learning is actually what makes that work well. So the better the machine learning is at predict how likely you are to click on something, the better this will work for everybody. For you, the user, because you don't see useless ads; for the seller, because their money isn't wasted; and for Google or whoever, because they make more money in that regard. So this, like the ideal, model of how economics works, in some sense, is actually being enabled by machine learning, literally at the rate of billions of auctions a day for just the case of ads.
Yeah, it's the technical term is it's reducing transaction costs of search costs and other types of things that make transactions less effective than they otherwise would be.
Exactly.
But just to stick with this matching for a minute, which is intriguing me, you hold out the promise, we'll talk about it in a minute, of a much vaster array of knowledge, but that could be accessible through machine learning. But of course, some of that is matching as well. Just don't normally think of it that way. So person who has cancer, God forbid, and has to figure out what treatment to use, that is a matching problem in a certain dimension, especially if you don't even know which medicines to search among. And there may be medicines to search among that aren't in existence yet. So you have to, in theory, figure out what those should be or could be, right?
Yeah, exactly right. So that is a great example because if, medical diagnosis a priori doesn't seem similar to these other things, but yet at a certain level it is very similar. In the same way that Amazon, recommends a book for you or Netflix recommends a movie, what a medical diagnosis system can do is recommend a drug for the particular thing that ails you. And cancer is a great example because, cancer is hard to cure because it's not a single disease, right? Everybody's cancer is different. And even the same person's cancer is different 3 months later because it mutated. And so the best solution is probably to have something like a machine learning algorithm that tries, given the patient's genome and their medical history and the mutations of the cancer, tries to predict what is the best, drug to treat that cancer. It could even be designing a new drug, which is also something that is done by machine learning, but that is very much how this works. Having said that, the problem of finding a good drug for somebody's cancer is much, much harder than the problem of finding a book or a movie to recommend. But, we're getting there.
Yeah, and the cost of a mistake, if I don't like the movie after 20 minutes, I'll turn it off. It's obviously a bad, ineffective drug is a lot more serious.
Exactly.
I have to say, I'm a very optimistic person, and I have a lot of faith in the human enterprise writ large, not so much in any one human. I have very little faith in any one human, so I'm suspicious of experts and power when it's centralized. But I'm very optimistic about the human enterprise. But you may be more optimistic than I am, which is impressive. Is all I'm trying to say. So I want to take this medical example for a moment. We've had guests on the program recently, Adam Seafu and Robert Aronowitz, who talk about some of the challenges of medical diagnosis and some of the ineffectiveness. And Seafu particularly talks about medical reversal, techniques, surgeries, devices that the empirical evidence suggests that they work well. Not only do not work well, they often are sometimes harmful. Machine learning can't solve that problem, it seems to me, and yet there's such a cheery tone to all of this. Do you want to react to that?
Well, actually, on the contrary. So, by the way, I am an optimist, but I think I also worry a lot about the things that might go wrong, and I actually think that's the right balance. I think we should be optimistic because the historical record justifies that. And if you're not optimistic, then you won't. If you don't try to improve things, you won't. At the same time, there are a lot of things that can go wrong, and we need to be continuously worrying about them. And the problem that you just mentioned is one of them. But actually, largely the cure for that problem is machine learning. Is that things have to be more evidence-based. The problem is that today there's a lot of surgery and treatments and whatnot that get deployed widely on the basis of very little evidence, on the basis of one little study on 1,000 people, there's this whole problem, as of reproducibility, yep. And these results just happen by chance.
Yep.
Exactly. So, but the solution for that is to be more evidence-based, is to have more evidence, is to have more trials, is to have, if we get the data from the patients as things are rolled out little by little, they never go from just 1,000 patients to, 10 million people in one step, and then people never looks at it again. Where medicine is going is that we are continuously getting the feedback from the results of treatments, and based on those results, certain things will rise or sink. And something that might have looked promising in the first study, if on the next 10,000 people it doesn't work so well, then we drop it. Or what might happen is that we realize, well, actually, this only works well for these 5% of people. But the machine learning lets us figure out which 5% it is, and then it's not used for the other 95, but for these 5 it is used. And again, these things are starting to happen, but we just need to move more in this direction despite the resistance from various directions. And by the way, this is not just in medicine. I think for every X, we should be doing more evidence-based X, right? Oh. Evidence-based policy, et cetera,
sure.
et cetera.
So, that's the question. Will the fundamental complexity of, say, the human body or the macroeconomy yield itself to the magic of machine learning? And I am somewhat skeptical. I like the idea that, yep, it hasn't worked so well so far. So in this particular area, say, whether it's machine learning or not, we just have to try harder. The question is whether it's ultimately doable or achievable or not, right? So
it may not be. So you're right. So, like machine learning can only learn things that are learnable. And there's, in fact, a lot of theory about what is learnable and about what is not learnable. And it is possible that, for example, the economy or the human body at some point are too complex for us to be able to predict it well. But remember, the goal in machine learning is not to predict perfectly. It's just to predict well enough to be useful.
Or better.
It's a little different from, the laws of physics. Let me give you a very extreme example. One of the oldest and most successful of applications of machine learning is in predicting, the stock market and foreign exchange fluctuations and things like that. And to predict whether stock will go up or down is extremely difficult. But if you are 51% accurate consistently, that's enough to make you very, very rich. If you come to me and say that you are 55% accurate, I think you're probably, making a mistake somewhere, or you're trying to con me. So just being slightly better than chance is actually enough to do well. And a lot of the most successful applications of machine learning were the ones where the starting point was very low. So my guess is that what's going to happen is, well, no, at the end of the day, we're not going to be able to predict the economy perfectly or the human body perfectly, but we're going to be able to predict them much, much better than we are predicting now and get correspondingly better results.
Yeah, I'm not so sure. I think it's something that's in the news these days, talked about before on the program, which is the impact of the minimum wage. So most of the attempts to assess the impact of the minimum wage on workers, on their wages, on their employment, of course, there are other aspects we tend not to talk about because they're not easy to measure. Their on-the-job training, the way they're treated during the day, politely or not. Those are things we don't observe usually. But the attempts to do that use traditional statistical methods, which the current generation of young econometricians are extremely optimistic and have solved most of the problems that were there in the past. Now, machine learning takes a very different approach, if I understand it correctly, from the statistical causation relationship ways that people have tried to measure impact in the past. So can you talk about that a little bit, you can talk about the differences between traditional attempts to assess relationships, such as regression analysis and statistics, and what machine learning might be able to provide that might be better?
Yeah, so I think there are two big differences. One is that the traditional statistical methods are very, very limited. They're things like linear regression. The only relationships that you can find are the ones that follow a straight line. And this will make you blind to most things that actually go on in the real world. Machine learning embraces the full gamut of nonlinear models. It's just, it's like having a Ferrari versus having a bicycle. There's really no comparison. And the other one is that traditional statistical analysis is based on very small amounts of data. It's like, let's make decisions about, the minimum wage based on some, aggregate data. That aggregate data has washed out most of the important details. In machine learning, you can make decisions based on data from all the individuals and treating them individual and seeing what will happen with them. And then finally, I think the way a lot of these big decisions will get made using machine learning is not that you do a big study up front and, decide what's going to happen, is that you start to deploy things a little bit here and there and see what happens and adjust according to that. And this is actually what all the companies on the web do. They do these things called A/B test and uplift modeling, which is basically trying out the two conditions, right? Do I have a minimum wage here? Do I not have a minimum wage there? And comparing how the two happen. And by doing that carefully, you can actually do not just correlation modeling, but actually suss out what causes what. And then you can take actions based on the causal connections that you discover that way.
So we should clarify, because we've been talking for a few minutes already. What are the differences between machine learning, big data, data mining, artificial intelligence? These are buzzwords that we hear, I think used probably interchangeably in many cases, which is not accurate. So can you talk about the differences between those?
Sure. So machine learning is a subfield of artificial intelligence. So artificial intelligence is the subfield of computer science that deals with, in some sense, the hardest problems. It's trying to make computers do the things that in humans require intelligence, like problem solving, vision, understanding language, common sense, understanding, etc., etc. Of all these capabilities, the most important one is the ability to learn. In fact, if we made a robot tomorrow that was as intelligent as a human but couldn't learn, the following, day would have fallen behind and it would never catch up again. So machine learning these days is very much at the center of AI.
Maybe for the people you hang out with, but yeah, I get your point. Not everybody learns every day, but I understand what you're trying to say there about it falling behind. Some people, they're pretty static.
No, but here's the thing, right? This is a very natural thought, but even when we human beings don't think of ourselves as learning, we are learning all the time. I'm talking about learning even at the lowest levels like perception. A lot of things that we don't even notice, that we take for granted. Those are actually the hardest things. It's one thing to be like learning to do a new job or learning to do something in a new way. Those in some sense are actually the hardest things for people to do. And you're right, many people just kind of like go along by that without learning much at that level. But I'm talking about much simpler things that we human beings take for granted, but those are actually the ones that computers have the most trouble with. And that this is what machine learning helps with. Like all the recent advances in computer vision and in speech recognition and whatnot, they were driven by machine learning. Those things that people don't understand often, why are the computers so bad at them? It's because they are learning all the time subconsciously, and the computers didn't know how. And we're still not as good at people at doing these things by any stretch, but we're getting there with the help of learning.
So I interrupted you. So machine learning is a subset of artificial intelligence. What do people mean when they say big data or data mining? They're very closely related to machine learning, though.
Yeah, so big data is just a lot of data, right? Yeah. And the relationship between machine learning and today's big data is tomorrow's data, right? What seemed like big data yesterday is just data now, and what seems like big data today, tomorrow will just be, the normal amounts of data. But there's a symbiotic relationship between machine learning and big data. Big data is, you can learn from small data. Right? You can learn from 1,000 data points or 100. It doesn't have to be 1 million or 1 billion. But as the amount of available data grows exponentially, the machine learning grows exponentially more powerful as well, just by piggybacking on that. And this is indeed very powerful because it means that where before, you could maybe program 1,000 rules by hand, today you can easily get 1 million by pushing a button and swallowing the data and inducing the rules from that. So the big data drives the machine learning. Machine learning also drives big data because at the end of the day, the reason to capture all that data and store it and clean it and process it is so that you can then go and learn models from it. So machine learning is what makes big data useful, and big data is what makes machine learning powerful. Data mining is a term that actually came from the business community. It was originally applied to this notion of, companies have large databases. There's probably lots of good information in there, along with maybe a lot of information that is not relevant. And the goal was to kind of like mine out the gold nuggets from that load. It's a term that's increasingly less used today. It's been largely replaced by data science, which is another buzzword.
It sounds bad.
but I think data science is a better word than data mining. Yeah. And the way I would describe data science is that it has machine learning at its core, but it also has all the high performance computing, parallel processing, on the one hand, information integration, and then things like visualization, reporting the results, interacting with the humans, use the system and whatnot. So it's the complete set of things that you need to have in order to, to make the most of the data that you have, whether it's in business or in science or in government or whatever.
So in the case of machine learning, it still struggles with this issue of causality. I just want to come back to this for a second, and then we'll move on. But it's often looking for patterns in the data. It's looking for matches. It's looking for similarities. It's looking for probabilities that something is more like something else. And ultimately, it can get better and better as it gets more and more data at seeing those correlations. But it fundamentally can't answer the questions of causation that we care about. And therefore, it is vulnerable.
No. Not true, right? No? Not true. This is what I was saying. This is actually a very common misconception about machine learning, is that it can only discover correlations. Machine learning can and does and has discovered causation, not just correlation. And as I mentioned before, this is actually happening as we speak. We all users of Google and Facebook and Amazon, you've probably, without knowing it, have probably been a part of, hundreds of these A/B tests whose goal is exactly to suss out what is the causal effect of making a change, for example, on the website. And they they're able to do that because it's experimental data, right? So from observational data that was just gathered for whatever purpose, it's often hard to suss out causality, although even in that case, there are techniques, that within some limits can discover causal relations from observational data. But let's set that aside. For the most part, causality, the way the scientists discover causality, is by performing experiments. And you can perform experiments with machine learning, and this is what all these, web companies do. They try out both conditions, and they see what the results are. And this is just what people were doing in medicine, decades ago, of, we'll have a control group of patients who don't take anything or a placebo. We'll have a control group of patients who take the actual drug, and then we see what the differences in the result are. People in computer science call this, A/B test, right? More generally, it's called randomized trials. But by doing randomized trials, you can suss out causality. But with machine learning, you can actually do a lot more than that. You can figure out not just, well, does this drug work or does it not work? You can figure out who does it work for. Who are the 5% of people for which this drug is a cure? Because you can then, you not only just look at the two conditions, but you look at all the other variables involved. So machine learning is actually an extraordinarily powerful way to discover causal relationships. It's just that most people haven't realized that yet.
Well, I have to disagree with you, and I'll make my case one more time. You can respond, and then we're going to move on. But in some of this, I suppose, is perhaps a somewhat philosophical disagreement. But randomized trials are often better than observational data, where we attempt to control for unobservables. But that doesn't mean there aren't unobservables in the randomized trials. Certainly, many randomized trial results do not generalize, have not generalized, and that's because we don't really understand the causal mechanism. So if you tell me that because this drug has worked on this set of people with these characteristics, it'll work on other set like people with the same characteristics, it might be true. It might be better than a random guess as to what would work for them. But if you don't understand the causal mechanism that's going on at, say, the cellular level, you don't know that these people really are similar to the other people. They're just similar observationally for what you have data on. You can't conclude that it's going to work for them, and oftentimes it doesn't. And we know that because we've seen these randomized trials fail to scale or fail to apply in certain different settings, and that's because there are, just as there are in observational cases, there's missing data on observables.
Yeah, this really boils down to what you mean by causality, right? And, there's, of course, a long, history of people discussing this in philosophy. But at the end of the day, I think it really is just the following. Causality is being able to predict the effects of your actions.
Yep.
If you know how to predict the effects of your actions, that's all that you need, right? And if, a notion of causality that does not involve predicting the effect of your actions, I'm not sure what it would mean or how it would be different from correlation. And so, all I'm saying is that you can use machine learning to predict the effects of your actions. Now, a lot of the problems that you're pointing out, they're very real, missing data, insufficient data, and so on and so forth. That limits how well you can do your causal, modeling.
Right.
And for example, in the case of cancer, is it enough to just have sort of like this high level, these drugs work on these patients, or do you really need to go down to modeling how the metabolism in the cell works and the gene regulatory networks and whatnot? And I think that at the end of the day, you need to go down to the latter, but we can get the data for the latter from, microarrays and gene sequencing and whatnot. And the former will get you some part of the way there, right? And there are a lot of, guarantees that you can establish that unfortunately a lot of these trials tend to fail, that will let you know with high confidence whether you have something that generalizes or not. I mean, the entire field of machine learning is all about how can I be confident that I have generalized well from the data that I have seen to the data that I haven't seen. And again, this is induction, it's not deduction, so it's never perfect, but it's far from, just picking up correlations.
So let's you divide the types of machine learning into 5 different kinds: symbolists, connectionists, evolutionaries, Bayesians, and analogizers. All of them are sort of attempts to mimic things we think the brain does in certain ways. It seems to me. Maybe that's not an accurate way to describe it, but talk briefly about each kind, if you would, and a little bit about how people who focus on those techniques, what are some of the ways that they look for, they use machine learning?
Yeah, so some of them mimic the brain, but the others very much don't. In fact, the people who do them would be very resistant to the notion that what they're doing is modeling the brain, because they think, the brain is just a pile of evolutionary hacks, and there's no guarantee that it's actually doing the optimal thing. So their goal is to discover the optimal thing straight out. So, to go through these, the connectionists are the people whose entire agenda is to do machine learning inspired by how the brain works, right? It's reverse engineering the competition. The brain is a network of neurons, so let's build a model of a neuron, connect it up in a network, and then try to learn the same way the brain does, which is by adjusting the strengths of the connections between the neurons, right? Everything that you know, everything that you've learned is encoded in how strong the connections between the neurons are. And the stronger the connection between, neurons A and B means that when neuron A fires, that makes neuron B more likely to fire. So the stronger the connection, the more neuron A will tend to make neuron B fire. And because all the knowledge is encoded in the connections, this approach is often, this school of thought is often known as connectionism. And they are inspired by the human brain, but only up to a point, because at the end of the day, it's machine learning, and the goal is to just learn however way we can. So at the end of the day, a lot of these connectionist algorithms, even though they were originally inspired by the brain, often wind up looking very different from what the brain does. And now another approach that is inspired by nature, although not the brain, is the evolutionary approach. And the idea there is that, evolution, that is the greatest learning algorithm on Earth, right? It created you and I, not just the brain, but every animal and plant, every living creature that exists. So why don't we try to evolve programs in the same way that nature evolves creatures? And we know roughly how evolution works, right? Evolution is very much an algorithm. It's a search algorithm. It's something that's very familiar to computer scientists, and indeed these days biologists do tend to view evolution that way. It starts out with a population. Each one of them performs the task. The ones that do best, the fittest, and then they get to mate with each other and they produce offspring. And then the next generation will be better at the task. And it turns out we can do amazing things that way. So that's the evolutionary approach. The analogizer approach in some ways is inspired by what people do, not the brain per se, but more at the level of psychology. It's reasoning by analogy. A lot of the people who read the book, they often say, yes, the analogizer approach, that's the one that really resonates with me.
It makes it easiest to understand, I think.
Yeah, it's easy. It's a very natural one, right? We do that all the time. Again, there's a lot of evidence from psychology. When we see a new problem, what we do is we try to, retrieve from our memory similar situations that we were in the past, and then we extrapolate the solutions. Like, say, I'm a doctor, I'm diagnosing a patient. I find the patient in the past that had the most similar symptoms, and I hypothesize that this patient has the same diagnosis. Very simple idea, but very powerful. So that's, doing things based on analogy. And it actually has inspirations from various quarters, but psychology is probably the single most important one.
You have to be careful. You could pick the wrong analogy.
Absolutely.
So that's
you could go wrong.
You could pick, it's really I always think of a CEO I once knew who confessed to me that his company went bankrupt because he picked the wrong Harvard case study. He was an Harvard MBA, and he quote picked the wrong one, whatever that means. I don't know what that's a strange, interesting way that he thought about his disastrous end financially. But I think that's the power of the case study approach, right? You say, oh, I see. It's just like, but of course sometimes you miss C, and that's the challenge of that.
And that happens all the time.
Yeah.
Even in history, right, a lot of the biggest mistakes were based on, the wrong analogies, like, oh, this war is like that one, so we're going to fight it the same way, and then guess what, it wasn't. So, you could pick the wrong case, or you could actually pick the right case but transfer the wrong things, right? Whenever you do an analogy between two things, some things are similar, some things aren't, and if you transfer the wrong things, it could also fall flat that way. Nevertheless, in practice, there are many things that are done very well with analogy. Like, one that people are familiar with is, these recommender systems. Like, you look for similar people with similar tastes, and you extrapolate from one to the other. Or things like call centers, right? You call up, Dell to say, my PC is on the fritz, and your problem is probably very similar to other problems that they've encountered before, so they can try to extrapolate. So yeah, this is a very interesting approach, and all of them have the pros and cons. Then there's the symbolic learning approach, and what the symbolists do is, again, this is more of a first principles approach. We're not necessarily trying to imitate people. We're just trying to formulate induction as the inverse of deduction. Right? In the same way that subtraction is the inverse of addition, deduction is going from general rules to specific facts. Induction is the opposite, but we can formulate it that way and solve it that way. Like, for example, if I tell you that Socrates is a human and humans are mortal, I can infer by deduction that Socrates is mortal, right? That's deduction. Well, the inverse of that is to say, what information am I missing if I know that Socrates is human in order to infer that he's mortal? And the information that you're missing is that humans are mortal. And so you can induce a rule that way. And this is very, very powerful because you can use different rules from different things, and then you can chain them together in new ways to answer completely different questions from the ones that you originally saw. And then finally, there's the Bayesians. The Bayesians come from statistics, and what they do is they try to formulate from first principles what is the optimal solution to the learning problem. And the way they look at it is like this. I have a range of hypotheses that I could use to explain my data. I have some amount, to which I believe each one of them a priori. I will always be uncertain about which is the right hypothesis, right, because induction is always uncertain. But what I'm going to do is I'm going to quantify the uncertainty with probability, and then as I see more evidence, I update the probability with which I believe each hypothesis. So the hypotheses that are consistent with the data will tend to become more probable, and the other ones will become less probable.
So one of the things I found is sort of a sub-theme of the book is that these different styles of machine learning have their ups and downs in the profession. So there are times when one of these five would look ascendant and the others look like they're not going to ever contribute anything again, but they often come back. And just comment on that. I found that fascinating.
I mean, exactly. So the machine learning has this amazing history, right, which is part of what I think made the book fun to write and hopefully makes it fun to read as well, is that, yes, on any given decade, it seems like there's one of these paradigms that's, sweeping all before it. But then come the next decade, the paradigm has fallen behind and another one is in the lead. And this is happening even as we speak. So right now, the dominant paradigm is connectionism. These days it's known by the name of deep learning, but deep learning is really just a type of connectionism. And this is actually the third coming of connectionism. Connectionism had its first heyday in the 50s and 60s, and then the symbolists basically killed it by showing that there were all of these important things that it couldn't do. And then it was dead for like 10, 20 years. And then it had another coming in the 80s, where some of those problems were solved, and then there were a lot of new applications that were possible. But then it kind of faded away again. The Bayesians kind of ruled for a decade, and then the analogizers ruled for another decade. But now guess what? The connectionists have come back again. So it'll be interesting to see what happens next decade. Maybe it'll be another one of these paradigms that comes up. Maybe connectionism really has taken off permanently, or maybe it'll be an entirely new paradigm, which to me would actually be the most exciting outcome.
Yeah, you argue that there's a master algorithm, a single unifying possible way to move forward that would allow us to invent everything that's ever been invented, learn everything that could ever be learned, and so on. So make the case for why you think that could be true.
Exactly. So that is what I think, is that none of these five paradigms is going to solve the whole learning problem. And the reason is very simple, is that each of these five paradigms has a particular problem that it deals with very well. And again, they've made a lot of progress there, but because all the five problems are real, there is no single algorithm that actually is going to solve all of them. So what you need to solve all of them is a unification of the five. And again, this is a very normal thing in science and in technology, is people develop all these different, models of different things, but then somebody else comes along and unifies them into one, right? The quintessential example of this is physics. Like, Maxwell, unified electromagnetism and electricity and magnetism and light. And today the standard model unifies three of the four main forces of nature, and there's things like string theory that hopefully will, unify them with the last one, which is gravity. So in a way, I think that what we need to look for, and what, a lot of us have been looking for in machine learning, is a similar grand unified theory of learning that unifies under one algorithm, all of these paradigms, that has all of the capabilities that each one of them has in a single algorithm. And then this algorithm will be able to learn all of the different things that these different types of learning are able to learn. And in principle, it will be able to learn absolutely anything. In fact, all of these, master algorithms from the individual paradigms, they have these theorems that say, if you give me enough data, I can learn any function. But it's one thing to say that in theory. It's another thing to do that with a reasonable amount of data and computing. And this is where we have a lot of progress to make. But this is also, I think, where we can at some point have an algorithm. And actually, I don't think we are that far from having an algorithm that is essentially as good as each one of these in its own domain, and therefore can replace all of them.
So, this desire for a grand unified theory is very human. We try to do it in a lot of areas. But just to take the most simple form of human interaction, which is sharing of emotions, right? So you and I don't know each other. We've never met. Here we are talking for the first time. We talked for about 4 minutes before this started. We joked around a little bit. And there's certain things I would say to you that I would not say to other people. But there's many, many things I won't say to you because, I don't know you. That I say for my family, other things I say for my spouse, other things I say to myself, and thank goodness they don't go out loud. There's a unique way of communicating depending on the circle of intimacy that I'm interacting with at the time. So why should I think that there's one general way of learning? Why isn't it possible that there's different ways for different problems?
No, so I actually agree with everything that you just said, but actually I think is somewhat orthogonal to the issue that we're talking about here, right? If we have a universal learning algorithm, first of all, it will only learn things that can be learned, and it will only learn what the data that it's given allows it to learn, right? At the end of the day, you still need to have the data to give to the algorithm so that it can learn the things that it will learn, right? Now, the question is, well, why should there be one and not many? The truth is that there are many, right? In the same way that there are many forces in nature, but you can unify them all into one model. So really, what a master algorithm does is it just shows what the relationships are between all these things. What are the ways in which this more general matrix can be specialized to each of these, right? And we don't know at the end of the day to what extent this can be done, but what we know from the history of science and technology is that this is a very productive enterprise. You often discover new things this way. You often are able to do things that you weren't able to do before. Even if at the end of the day, think about it this way, most problems, it's an 80-20 rule, right? So there's 20% of the work that does 80% of the job. And the master algorithm is not going to make, engineering or specializations of different things unnecessary. It's just going to do 80% of the job. Let me give you an analogy, not from science, but from technology. Think of the microprocessor. Right? There's nothing more important to the information age than the microprocessor. A microprocessor is actually a very weird thing. It's one circuit that can be programmed to do anything. Before there were microprocessors, people had to build a different design and fabricate a different digital circuit for every job. And then one time Intel had this Japanese company that wanted them to build 12 chips for 12 different things very quickly, and Intel was like, we can't do that. Let's just do one chip and then program it to do the different things. Now the thing about the microprocessor is that a microprocessor is not the best way to do anything. Whatever the problem is, there's always what's called an application-specific integrated circuit that will do it better than the microprocessor. And yet, microprocessors are what we use to do 99.9% of things, precisely because it's just one thing, and everybody can have it on their desktop or in their smartphone, and then it's just a matter of programming it. So we do sacrifice some efficiency, but at the end of the day, it's what we use for everything. And really, the master algorithm is really just for learning the same idea that a microprocessor is for integrated circuits.
So I'm going to read a somewhat lengthy paragraph that charmed me from the book, and then I want to ask you a philosophical question about it. So here's the passage. Quote, "If you're a parent, the entire mystery of learning unfolds before your eyes in the first 3 years of your child's life. A newborn baby can't talk, walk, recognize objects, or even understand that an object continues to exist when the baby isn't looking at it. But month after month, in steps large and small, by trial and error, great conceptual leaps, the child figures out how the world works, how people behave, how to communicate. By a child's third birthday, all this learning is coalesced into a stable self, a stream of consciousness that will continue throughout life. Older children and adults can time travel, a.k.a. remember things past, but only so far back. If we could revisit ourselves as infants and toddlers and see the world again through those newborn eyes, much of what puzzles us about learning, even about existence itself, would suddenly seem obvious. But as it is, the greatest mystery in the universe is not how it begins or ends or what infinitesimal threads it's woven from. It's what goes on in a small child's mind, how a pound of gray jelly can grow into the seat of consciousness, close quote. So I thought that was very beautiful. And then you imagine something called Robbie the robot that would somehow simulate the experience and learn from in the same way a child learns. So talk about how Robbie the robot might work, and then I'll ask my philosophical question.
Yeah, so, there are several approaches to solving the problem of AI, right? So how can we create robots and computers that are as intelligent as people? And, one of them, for example, is to mimic evolution. Another one is to just build a big knowledge base. But in some ways, the most intriguing one is this idea of building a robot baby, right? The existence proof of intelligence that we have is human beings. In fact, if we didn't have that, we wouldn't even be trying for this. So the idea the path, one possible path to AI, and the only one that we know is guaranteed to work, right, is to actually have a real being in the real world learning from experience in the same way that a baby does. And so the idea of the robot baby is let's just create something that has a brain, but it doesn't have to be at the level of neurons, right? It's just at the level of capabilities that has the same capabilities that the brain, that the mind, if you will, of a newborn baby has. And if it does have those capabilities and then we give it the same experience that a newborn baby has, then 2 or 3 years later we will have solved the problem. So that's the promise of this approach.
So the philosophical thought I had as I was down in the basement the other day with my wife, we were sorting through boxes of stuff that we don't look at except once a year when we go down in the basement and decide what to throw out and what to keep. And one of the boxes that we keep, even though we never examine it except when we go down to the basement the once a year to go through the boxes, it's a box of stuffed animals that our children had when they were babies. And we don't want to throw it out. I don't know if our kids will ever want to use them with their children. If they have children, our kids, we don't have any grandchildren, but I think we imagine the possibility that they would be used again. But I think it's something else is going on there. And if our children were in the basement with us going through that and they saw the animal or the stuffed item that they had when they were, say, 2.5 or 3 years old that was incredibly precious to them and, of course, has no value to them whatsoever right now, they would have just as we have as parents, they would have an incredible stab of emotional reaction, a nostalgia, a feeling that I can't imagine Robbie the robot would ever have. Am I wrong?
I don't know. So this is a good question, right? So there's actually several related questions here. One is, would Robbie the robot need to have emotions in order to learn? I actually think the answer is yes. And will it have those emotions? I think at a functional level, we already know how to put the equivalent of emotions into a robot because emotions are what guides us, right? We were talking before about goals, right? Emotions are the way evolution in some sense programmed you to do the right things and not the wrong ones, right? The reason we have, fear and pleasure and pain and happiness and all of these things is so that we can choose the right things to do. And we know how to do that in a robot, right? The technical term for that is the objective function or the utility function.
Yeah. But it's not,
now, whether
it's not the same,
at the end of the day... Mm-hmm.
Doesn't seem the same. Maybe it would be. I don't know. I guess that's a tough question.
Exactly. So, yeah. So functionally, in terms of the, input-output behavior, I think this could be indistinguishable from the robot having emotions. Whether the robot is really having emotions is probably something that we will never know for sure. But again, we don't know if animals or if even other people have the same emotions that we do. We just give them credit for them because they're similar to us. And I think that in practice what will happen, in fact, this is already happening, with a lot of these, chatbots, for example, is that if these robots and computers behave like they have emotions, we will treat them as if they have emotions and assume that they do. And often we assume that they have a lot more emotions than they do because we project our humanity into them. So I think at a practical level, maybe at the end of the day, it won't make that much difference. There remains this very, fascinating philosophical question, which is what is really going on in their minds? And I don't know if or in our minds, for that matter. I'm not sure that we will ever really have an answer to that.
I've raised the question recently on the program about whether consciousness is something that is amenable to scientific understanding. The certain philosophers, David Chalmers, Thomas Nagel, claim, and they're both atheists, but they claim that models of evolution and the standard models of biology, chemistry, and physics cannot explain human consciousness. Have you read that work? Have you thought about it at all?
Yeah, and I think that I disagree with them at the following level. I think, if we fast forward to 50 years from now, we will probably have a very good and very satisfying model of consciousness. It'll probably be using different concepts than the ones that people have from the sciences right now, right? The problem is that we haven't found the right concepts to pin down consciousness yet. But I think there will come a point at which we do, in the sense that all the psychological and, and neural correlates of consciousness will be explained by this model. And again, for practical purposes, maybe even for philosophical purposes, that will be good. Now, there is, I think, a hard, what is often called the hard question of consciousness, which is, at the end of the day, because consciousness is a subjective experience, you cannot have an objective test of it. So in some sense, once you get down to that hardcore, consciousness is beyond the scope of science. Unless somebody comes up with something that I don't quite imagine yet, I think, again, what will probably happen is that we will get to a point, probably not in the near future, it'll be, decades from now, where we understand consciousness well enough that we are satisfied with our understanding, and we don't ask ourselves these questions about it anymore. But, I can, find analogies in the history of science for similar things that used to seem completely mysterious. Like, life itself used to be completely mysterious, and today it's not that mysterious anymore. There's DNA and there's proteins and there's, what's called the central dogma of biology. At the end of the day, that the irreducible mystery of life is still there. It's just that, it's really not that prominent on our minds anymore, because we feel like we understand, the essence of how life works. And I think chances are the same thing will happen with consciousness.
So let's talk about some applications, as you do at the end of the book, which are extremely interesting. Let's start with this idea that by knowing something about how websites and my browser is learning about me through my behavior, I can structure my relationship to my computer and to the web and to my browser perhaps more effectively. What are some of the things I should be thinking about and being aware of?
Yeah, so, where we're going with machine learning is that machine learning will allow everything to be personalized to you. Right? Think of all the different devices that you interact with. And again, it starts with computers, but it goes well beyond that into houses and cars and whatnot. And they should all be adapting themselves to you without you having to do anything. Right? Here's one way to think of this. Technologies are like superpowers, like telephones let you communicate at a distance, airplanes let you fly, and machine learning is another superpower. And what is that superpower? It's the superpower of having the world adapt itself to you without you having to do anything. Now, what happens right now is that we just have these little nuggets of that adaptability here and there. So, Amazon will recommend things for you, and and your phone will learn to recognize, how you speak, and so on. But really, where this is going, and where I think we want it to go, is where you actually have not just all these little models of you that different companies have based on the little sliver of your data that they've gathered. It's that all of your data goes together into one big model that sees all aspects of you, right? Sees you, it's like a 360-degree view of you. And then that model will be, your faithful companion for everything that you do at every stage of your life. When you're going to college, when deciding, what colleges to apply to, preparing for the tests, looking for jobs, looking for soulmates, looking for whatever, it'll be kind of like your best friend, and it will know you in some ways as well as your best friend. Now, of course, I think we will want to have that. There's a one big barrier to that, which is I don't think we'll want that model of us to be owned by Google or Apple or whoever, right? Because that would give them too much power. So I think things need to be done in a different way from what they are done today, so that I can feel like there's, like I can have, this model of me that will only ever be used on my behalf and not to exploit me or sell me something.
Yeah, I can't help but think of my brother and his wife when they got married. Their song was "It Had to Be You," and the last verse of that song, I think, is very apt for many of us in our marriages and our relationships, our friendships. It goes like this: "Some others I've seen might never be mean, might never be cross or try to be boss, but they wouldn't do, for nobody else gave me a thrill. With all your faults, I love you still. It had to be you. wonderful you, it had to be you. So are you going to say that, we get annoyed now when our cell phones go out, when Siri misunderstands us, when the spell checker doesn't realize that I'm typing in Hebrew and that's really the word I meant. Would you leave it alone? And so our lives get easier. Like you say, it should be tailored to us, and it will get increasingly easier, right? Our cars are going to there's incredibly wonderful things are going to happen, but a huge part of our life is full of surprises. Or is your answer going to be that, oh, yeah, well, we'll program a soulmate who's imperfect in the right way?
Well, no, so life is full of surprises. And first of all, again, machine learning can only learn what can be learned, so there will always be surprises, number one. But number two, if you have this kind of like this digital, avatar that kind of like does things for you on your behalf, some of its job will be to bring in new things. Right, it will be to not, let you just lock yourself up in this world where things are always predictable. Right, that wouldn't be doing a very good job. But now, I think the example with the song that you gave is actually a very good one. Right, why do people, husbands and wives and so on, feel like that? Is it because it really had to be you, or because they hit it off? And let me put it this way. One of the hardest applications of machine learning is actually this application of finding, dates for people. And part of that is that whether or not two people will hit it off is actually not just a function of who they are. It's a function of how things went, right? Two people meet on their first date and, maybe things go very well and they wound up feeling like they were made for each other, even though they really weren't. They're just so in love with each other that's how they feel. That same two people, the conversation could have gone on a different track and they could have annoyed each other and decided that, no, they didn't like each other and never ever see each other again. So there's this degree of sort of like unpredictability, because humans are very complex. Now, how would the dating, learning system of the future deal with this? I think that, imagine that it has a very good model of both of these people, right? Or of each, of all people, and again, it's trying to match them, to go back to what we started out talking about. What it's going to do, I think, is it's going to run 1,000 simulated dates between every pair of people. And then it's going to recommend the ones that had the highest percentage of success. With this woman, 95% of the time you were just like, you really hit it off. Yeah.
Of course, the machine learners will when they're in the 5%, when they have a miserable time and they keep trying and they're still miserable, they're going to say, well, I'm going to trust the algorithm. Other people are probably not going to trust the algorithm and they're going to make their own decisions. But it's a fascinating question. It doesn't have a simple... There's no real answer, of course, of what will ultimately come from that, but it's really quite extraordinary. I love when you wrote, here's another quote from the book, people worry that computers will get too smart and take over the world, but the real problem is that they're too stupid and they've already taken over the world. Explain what you mean by that and why you're not worried about some of the issues we've raised on this program before with Nicholas Bostrom and others, that AI is this, perhaps the greatest threat to humanity. Machine learning could destroy the world, et cetera.
Well, exactly. I think those worries are misguided, and frankly, I don't know too many actual AI researchers who take them too seriously, right? They're based on this confusion between AIs and people, right? Because humans are the only intelligent creatures on Earth, when we think about intelligence, we tend to confuse it with being human. But being intelligent and being human are very different things, right? In Hollywood movies, the AIs and the robots are always humans in disguise. But the real AIs and robots are very different from humans, notably because they don't have goals of their own. People have this model of like, there'll be a different set of agents who are competing with us for control of the planet. They're not going to be competing with us for anything because we set their goals. Their intelligence is only being applied to solve the problems that we set them to solve, like cure cancer. And the more intelligent they are, the better. People have this worry that, we're going to make computers too intelligent and then they'll take over from us. And the thing that worries me is that, the way that computers do a lot of damage today is by being stupid. Is that like they're making decisions about who gets credit, about who's a potential terrorist, about, potential dates and whatnot. And they make mistakes all the time because they don't know any better. This is the real damage that computers do. The cure for that is to make them more intelligent so that they will really understand what we're telling them to do, so that they'll have common sense, so that they will do a better job than they do today. So, so the real problem is that they're too stupid and they've already taken over the world.
So I know some people in the AI community who are very worried about the singularity. They do worry that things are going to go out of control. So talk about how your book has been received among not the general public, but among your colleagues in the machine learning world. Are they as optimistic as you are about the master algorithm potential to find it? And are they as optimistic as you are that we shouldn't worry about machines getting running amok?
Yeah, so the great majority of AI researchers do not believe in the singularity. In fact, they think it's kind of a ridiculous idea, maybe more so than they should. But actually, the reaction that I had from a lot of people in the community, even when they found out that I was writing this book, was, "Oh, thank God! Finally, somebody's going to write a serious book about AI, as opposed to things like the singularity." So in that regard, I think the reactions has been very good. I think this notion of the singularity, that there's going to come a time when we don't understand anything anymore, frankly, it's a little silly, because we never understood the world, more than a little bit. The difference is that now some of the things that we don't understand are actually created by us. But that already happens, right? It's like if the singularity is computers doing things that people don't understand, this already happens, and the world hasn't collapsed because of that, precisely because we design it to keep an understandable interface to us, because at the end of the day, it's all there to serve us. So in some ways, I think, it's odd that the people who really worry about the singularity, like people like, Elon Musk and Nick Bostrom, they're on the one hand overly optimistic, I think, about how quickly and how far we'll get with AI, but also overly pessimistic about what the consequences of that will be. I think the reality is more that this is a long, we're in this for the long haul, right? We've come 1,000 miles, but there's 1,000,000 miles more to go. And there'll be exciting progress at every stage, but it's a long road. And at the same time, if you look at every technology, and AI is going to be no exception, yes, there's potential for things to go wrong and for people to make bad uses of it and whatnot. But in the end, the good, far, far outweighs the bad. And I don't think that's going to be different here.
And finally, why don't you talk about you have an optimistic vision of how we spend our time. I think a lot of people worry we're not going to have any jobs. Robots are going to figure out all the things that we can do. They'll do them better. And the only people who will be rich will be the people who build the robots. And the rest of us will sit around with nothing to do. You have a different vision. I'm sympathetic to it. How do you see things going?
Yeah, I think, so this is a very salient question, of course. I think that in the near term, people are a lot more worried about jobs than they really should be, right? So computers will do more and more things, but people will do things with those computers. So most jobs will not disappear. They will just be changed by the fact that people will not be doing them with the help of machine learning algorithms. So the question is more like, what are the parts of my job that I can automate, the boring parts, the parts that I don't want to do, such that I can then do the more interesting parts? Here's I think what is a very good example. Deep Blue beat Kasparov, and now the world's greatest chess player is a computer, right? No, wrong. Even now, 20 years after Deep Blue beat Kasparov, the world's best chess players are not computers. They are teams of humans and computers. A human with a computer can beat a computer because humans and computers have complementary strengths and weaknesses. And I think the same thing is going to be true for a lot of jobs. And also this, like as always with automation, it's always easier to see the jobs that get lost than the ones that are going to get created. Because, things will become cheaper, so there'll be demand for complementary goods. People will just have more disposable income that they will use to buy other things. There will be whole new categories of jobs that are created, right? Like in the 19th century, most Americans were farmers, and then all those jobs disappeared, but, it's not like 95% of Americans are unemployed. They're just doing things that were unimaginable back then, like app designer, right? There's millions of people who make a living designing apps. So I think in the near term, I think people do worry too much about this. But let's imagine, because we should for just a second, if there is a future where, robots and computers can do everything better than people, what will happen then? And again, I think, there will be a gradual path towards that. I think that's what's going to happen is very simple, is that it's one thing when the unemployment rate is 5%. Once the unemployment rate is 50%, everybody is going to vote for very generous unemployment benefits or for, distributing the wealth, right? In a democracy, everybody has a vote. And once 95% of the people are the ones that would be on the receiving end of this, universal basic income or such, I have a hard time seeing that not happening. right? There are certain things that can happen because they fly under the radar, but something like this would not be like that. And again, people are already talking about things like having a universal, basic income. It's, of course, a controversial topic, but I, for one, actually think that even today would already be better to have something like that than to have the patchwork of, all these different things that, many of them very inefficient, subject to capture by different, special interest groups. It would be better to have a sort of like simpler and more uniform solution. And then what the level of that basic income is, well, that can change depending on the progress of technology, depending on the economic conditions and the politics and so forth.
My guest today has been Pedro Domingos. His book is The Master Algorithm. Pedro, thank you for being part of EconTalk.
Thanks. This is great.
This is EconTalk, part of the Library of Economics and Liberty. For more EconTalk, go to econtalk.org, where you can also comment on today's podcast and find links and readings related to today's conversation. The sound engineer for EconTalk is Rich Goyette. I'm your host, Russ Roberts. Thanks for listening. Talk to you on Monday.